Hello everyone from Math 2000, Linear Algebra. It's Professor Winson here again with a video on your ZyBooks Section 4.1 titled Introduction to Determinants. Now the determinant of a square matrix is a number, and it's a number that's going to help us determine whether or not that matrix has an inverse, right? Whether or not it's invertible. So that's what the whole chapter is about. Chapter 4 is the finding of these determinants, and then also some applications of them, the uses for them. Alright, so I'll start here. Now again, you can read the summary and the objectives. So the determinant, again, is just a number associated with the matrix. And it's going to be associated with a square matrix, right? So a 2 by 2, a 3 by 3, 4 by 4, etc. So if a matrix is not square, we're not going to find the determinant of that matrix. It won't have a determinant. So I'll read this off here for you. The determinant of a square matrix A, denoted by either det A or det of A, determinant of A, or determinant of with the brackets around A, or now this last one I'll probably write more often because it's shorter. It looks like the absolute value of A, but if A is a matrix, it means the determinant of A. All right, and as I mentioned, this is a numerical quantity calculated using the entries of the matrix. One common use of the determinant is to determine whether the system of equations represented by a square matrix has a unique solution. Or in other words, is that square matrix invertible or not? If the determinant is 0, the system does not have a unique solution. And like I said, the determinant can also be used to determine whether a square matrix has an inverse. Right? And the inverse of the matrix multiplied by the original matrix results in the identity matrix. We've seen that before. Multiplying a matrix by the corresponding inverse is therefore analogous to dividing a real number by itself. Right? Since using the inverse is analogous to division, finding the inverse of a matrix whose determinant is 0 is similar to trying to divide by 0. Thus, a determinant of 0 means that a particular matrix does not have an inverse. Right, so, if a determinant is 0, no inverse. If a determinant of a matrix, a square matrix, is not 0, then it will have an inverse. Okay, keep that in mind. Alright, now the determinant of a 1 by 1 matrix is simply that entry. Right, a 1 by 1 matrix has one entry, so it's simply that entry. And what we're going to see in this section is the determinant of a 2 by 2 matrix, a little formula for it, and the determinant of a 3 by 3 matrix. And then in the coming sections, we'll see how to find more general determinants, right? The determinant of a 4 by 4, 5 by 5. All right, because in this section, in section 4.1 here, the way you find the determinant of a 2 by 2 matrix and the way they're going to show you how to find the determinant of a 3 by 3 matrix are very specific to 2 by 2 and 3 by 3 matrices only. All right, and we're going to see in the coming sections, right, sections later in this chapter, we're going to see a more general method for finding determinants of larger or just any square matrix. Right? Okay, so for a 2 by 2 matrix, say this matrix like A, B, C, D, right? You see the little bar, again, the little looks like absolute value symbols, means determinant. do you remember when we were finding the inverse of a 2 by 2 matrix? There was that little formula where I did like the cross products here. You did A times D, right? You multiplied the entries down the main diagonal and then subtracted the product of the other two entries, B times C. So A times D minus B times C. This number, AD minus BC, now has a special name, and I think I mentioned the word determinant in that section on the inverse of 2 by 2 matrices. But this is called, the determinant of a 2 by 2 matrix. And as mentioned before, if this is 0, then this matrix has no inverse. If this is not 0, then it has an inverse. And again, you've seen the formula. You've seen the inverse of a 2 by 2 matrix. Okay, so I'll just go through these examples here, right, on a piece of paper. Find the determinant of each 2 by 2 matrix. Okay, so here I've written both of the matrices in question, and I'll start with this first one, matrix A. Now you could write it again this way, the determinant of A, or again, just to save on a little writing here, it looks like right, the absolute value of A, but it means the determinant of A. You should know that because A is a matrix here. Like I said, very simple calculation, and I like to make this little diagram here. You take the product of the main diagonal entries, so it's going to be 2 times 1, and then kind of loop around, and then you come outside here and come back down, and put a little minus sign out here. We're subtracting, and then the product of the other two entries. Right, so 2 times 1 minus, and then 5 times 3. Okay, and 2 times 1 is 2, minus 5 times 3 is 15. 2 minus 15 is negative 13. Alright, so the determinant of matrix A here is negative 13. Now, this is not 0. Right? Negative 13 is not 0. And that tells me that A inverse, right, A inverse exists. And we should, and again, based on stuff done in chapter 3, you should be able to tell me what A inverse is then. Right. Okay, and then the second matrix they give me, the second 2 by 2 matrix, same procedure, right? It's take the product of the main diagonal entries, so negative 4 times 7, and then loop around here, and then minus the product of the other entries, 10 and negative 6. So the determinant of matrix C, or again DET of C, is negative 4 times 7 minus 10 times negative 6. Right. So this is negative 28 minus, negative 60. Well, that would be plus 60. So negative 28, plus 60 be positive 32. All right, so the determinant of C is positive 32. And again, this is not 0. All right, so since this determinant is not 0, the matrix C inverse would exist. Right? This matrix C is invertible. It is what they call non-singular, and that means you should be able to find what C inverse is. Okay. Hopefully that's simple enough for a 2 by 2. Now let me also show you. You can punch this up on your calculator. Right? Again, TI 83, 84, very similar. So if I go to that matrix menu and over to edit, I'll make a matrix. So I'll make matrix A here, and I'll just make matrix A this 2 by 2 matrix right here. So I enter the size. You've seen me enter a matrix before. And the entries, 2, 5, 3, and 1. All right, then I get out of here, I go quit. Then on the main calculation screen, I go back to the matrix menu, over to math, and you see the very first thing, the very top, it says DET. That's determinant. So enter, see the determinant of, what matrix. So second matrix, and then matrix A, right, matrix A. And hopefully it'll spit back at me negative 13. And it does, look at that. Alright, so you can have the calculator do it for you, but I would say have the calculator do it as a check. Alright, I do want you to learn how to do these, determinants of square matrices by hand, and then use the calculator to check that you did the work correctly. So it looks like I did okay on matrix A there, and you can enter matrix C separately and figure that one out. Okay, so those are 2 by 2 matrices. Right, now they have a few other ones here. Right, I'll just do this first one. What's the determinant of, they got the entries written here. So it'd be 30 minus 30. The determinant is 0. And that means that this matrix has no inverse. Alright, this matrix with entries, 3, 5 in the first row and 6 and 10 in the second row, this matrix has no inverse. And I'll leave the next one to you. Pretty easy. And again, same thing here. Look, there's only 2 of these. This is 9 minus 24, right? 1 times 9 minus 4 times 6. 9 minus 24 be negative 15. Check and hooray. All right, real simple, I think. Real simple calculations for the determinant of a 2 by 2 matrix. All right. So the next part of this section might take a little longer. Of course, it's a larger size. The determinant of a 3 by 3 matrix. Alright, so the determinant of a 3 by 3 matrix can be found by writing the matrix elements in order with the first 2 columns repeated. So you see how they have the 3 by 3 here. Oh, move the picture. See, there's the 3 by 3, the first 3 columns. And then you see the next 2 here, they're just repeating the first 2 columns. They write A11, A21, A31 again. And then they write the second column again, A12, A22, A32. And then, see my little arrow diagram here. You multiply starting in the upper left corner, you multiply the entries down each of these diagonals here. So A11 to A33, then A12 to A31, A13 to A32. Right, you take all those products and add them up. Then you subtract all the dotted ones, all these other going backwards, starting from the upper right corner and multiplying these 3 diagonals, these 3 diagonal entries, these 3 diagonal entries, and subtracting all of those, and you get this formula here. Alright, so it's a crazy formula. I wouldn't recommend memorizing it or anything. But you see it says multiply the elements along each arrow, right, each solid arrow. The products produced along the solid arrows to the right are added. The products produced along the dashed or dotted arrows to the left are subtracted. Right. Now, this is the only way they show you how to find the determinant of a 3 by 3 matrix in this section. But like I mentioned at the beginning of the section, this method they're showing you here, this is not the only way to find the determinant of a 3 by 3 matrix. It's just probably the easiest. This is probably the easiest way. But what we're going to see in coming sections are other methods, a more general method for finding the determinant of any square matrix, not just a 3 by 3. Oh, and one more thing. this procedure they're doing where they're copying the first two columns, this is only good for a 3 by 3 matrix. This is not good for you can't do this kind of method with a 4 by 4 or a 5 by 5 or a 6 by 6. This procedure they're doing here is only valid for a 3 by 3 matrix. Please keep that in mind. Alright, so I'll do again these couple examples here on some paper and show you this procedure that they're doing to find the determinant of a 3 by 3 matrix. Alright, so here's the matrix A that's given to me. Now, this procedure, this method for finding the determinant of A, the determinant of a 3 by 3, starts off this way. So I've got this 3 by 3 here. Then I do a little addendum, a little addition over here. I add on, I just recopy the first two columns. So I recopy the first column, 1, 3, 4, and I'm doing it in a different color so that you know it's not actually part of the matrix. And then next to that, I also copy the second column, 5, 0, 6. Alright. Now come all these diagonals. Alright. So starting in the upper left corner, I'm going to multiply 1 by 0 by 8, down that diagonal. And then I'm going to add to that 5 times 7 times 4. And then I'm going to add to that 2 times 3 times 6. Okay. And then I'm in the lower right corner. I can't go any further. Right. So I'm going to start off, the determinant of matrix A is, again, the sum of these products. 1 times 0 times 8 plus 5 times 7 times 4 plus 2 times 3 times 6. Okay, and we'll figure out what those products are in a second. Alright, so all those that are falling, these diagonals that are going down and to the right, you're adding all those. Okay. And then you subtract, starting in the upper right hand corner, the 3 diagonals going down to the left. So 5, and I'm going to make these like this is just a different little dashed arrows. Okay. So 5 times 3 times 8. Then subtract 1 times 7 times 6. Then subtract 2 times 0 times 4. Right, doing the dotted, these diagonals that are going down and to the left. So down here, I'll go minus 5 times 3 times 8. Minus 1 times 7 times 6. And then finally minus again 2 times 0 times 4. Alright. And then we'll figure out these products. Alright. Now, anything with a factor of 0 there is going to be nothing. Alright, so this product is 0. I'm not going to write it again. This product is also 0, right, so I'm not going to write that again. But all the other ones have some value. Alright, so this is 5 times 7 times 4, that's 20 times 7, that's 140. Plus, this is 36, right? And then we have the minuses. Minus, this is 40 times 3, so 120. And then I got another minus here, and then this is just 42. Alright, and then putting everything together. Now 140 minus 120 is just 20. Plus 36 would be 56. And then 56 minus 42 be 14. Okay, so the determinant of this 3 by, no, I mean, again, ignore the columns that I copied. The determinant of the 3 by 3 matrix A that we started with is 14. And again, this is not 0, meaning that A inverse exists. Okay, if it were 0, it wouldn't have an inverse. All right, and let me double check that. I'm going to bring up the calculator. Enter this 3 by 3 matrix. Let's go to matrix A again. So we had 1, 5, 2 in the first row, 3, 0, 7, and 4, 6, 8. And the reason I just changed matrix A is because I already have the determinant of A up. So I'll just re-enter that second entry. And look at that, it's 14. All right, so I did this correctly. Yeah, so you copy the first two columns again, and then starting in the upper left-hand corner, you add the products of the three diagonals going down to the right, and then starting in the upper right-hand corner, subtract the product of the three diagonals going down to the left, and get your final number that way. All right, so it takes a while. Right? It wasn't nearly as fast as the 2 by 2. And I will make a note for you, and I know I said this out loud a second ago, but this method of copying columns and doing these diagonals, this method for finding a determinant is only good for a 3 by 3 matrix. Okay, so in the later sections, when we start looking at larger matrices, 4 by 4, 5 by 5, 6 by 6, etc., this procedure won't work. Okay, this is only good for a 3 by 3 matrix. All right. All right. So I'm gonna leave. I'm not gonna do B here. I'll let you read what they see. They got the sum, a bunch of sums, and then minus, minus, minus. Right. All these products of the diagonal entries after copying the first two columns next to the matrix. And then again, you can double check with your calculator. All right. All right. So I'll do I'll do one more of these. All right. So let's take a look at this matrix here. All right, so this is again the big bar. It looks like absolute value bars means determinant. So yet again, it's a 3 by 3. I'll do that same procedure they showed us. All right, copy down the first two columns out here. So 3, 2, 4 again, and then 0, 7, 6. And then 3 times 7 times 0 plus 0 times 5 times 4. I mean, the nice thing is that there's some zeros in this to make the calculations a little easier. Plus 1 times 2 times 6. All right. And then we will subtract 0 times 2 times 0 minus 3 times 5 times 6, and then minus 1 times 7 times 4. All right, so I'll just write out those products now. So this says determinants equal to 0 plus 0 plus 12. So 12, and then minus 0 minus, this is 90, and then minus 28. All right, now negative 90 and negative 28, all right, that would make negative 118, and then put a positive 12 on that, that'd be negative 106. And if you want to use your calculator again, put in that 3 by 3 matrix and double check, be my guest. But this is should be, if I did everything correctly, negative 106. Great. And again, it's not 0, so that 3 by 3 matrix with these entries would have an inverse, and you should be able to find it. I'll leave that to you. And then you got some more down here. Now there's only a couple of these. So again, you're going to hit start, find the determinant of this 3 by 3 matrix with that procedure where you're copying down the first two columns, doing the 3 diagonals that go down and to the right, adding those up, and subtracting the products of the 3 diagonals going down and to the left. So I'll leave those to you. Alright, now some application of this is determining if 3 points are collinear. Right, use the determinant to determine if 3 points on the xy coordinate plane are collinear, right? Are they on the same line? So you're going to be setting up a matrix and finding its determinant. And if the determinant is 0, you'll see that the points are on the same line. And if the determinant of this matrix here is not 0, then the points are not on the same line, not collinear. Alright, so the points x1, y1, x2, y2, and x3, y3 are collinear, right? They fall on the same line if and only if the determinant of this 3 by 3 matrix, where you have, x1, y1, x2, y2, and x3, y3, you put the coordinates of the points going down and in the first two columns, and then the third column is made up of just ones. If the determinant of this matrix is 0, the 3 points will be collinear. Alright, now I know you could probably figure this out without a matrix and without determinants. Let me show you what I mean, right? This is just a basic algebra concept. So here, I'll just do number 1 here on paper. Okay, you're asked, are these 3 points on the xy plane, are they collinear? Right? Do they fall on the same line? Now, you could do some investigation work, some exploring. Now this isn't going to be perfect because I'm doing this by hand, but I'm going to try to make all my notches as evenly spaced as possible. So you got the point 1, 5, right? So there's 1 unit and then 5 units up. Alright, so there's the point 1, 5 right there. Then -3, -2. So again, trying my best to make this look, these notches, as evenly spaced as possible. And so there's -3, -2. Now, any 2 points will always be on a line, right? You can always draw a line through any 2 points. But then is this third point, also on this line? Right? So I'm gonna actually draw this line here. I don't know why I'm bringing out a ruler now, but let's draw this line through the first 2 points. All right, there's a line. And then the big question now is this third point also on this line? -1, 2. Now again, -1, 2. It looks like it based on my drawing. They look collinear, but this was a crappy hand drawing. I don't know if I messed up on my spacing. Now, if they were truly collinear, right? If they were collinear, then the slope of the line going through these 2 points should be equal to the slope of the line going through these 2 points, right? So the slope, remember how to calculate slope. Slope is the change in y over the change in x, right? So 5 minus -2, change in y, divided by the change in x, 1 minus -3. that slope, the slope of the line going through these 2 points, should be equivalent to the slope of the line going through these 2 points, if they truly are on the same line. So the big question is this slope equal to this slope? Now the slope of the line going through these 2 points would be, a change in y, -2 minus 2, divided by change in x, -3 minus -1. Alright, so here this is 7 in the numerator, 4 in the denominator, and this is -4 in the numerator, and -2 in the denominator. So I said they look collinear, but again, this is a hand drawing. Looking at this, you can tell that they are not. All right, watch this. Right, -3 plus that's -3 plus 1 is -2. So this is 7/4. This is just the number 2. Right. Is 7/4 equal to 2? No. The answer is no, right? So these are not collinear. This is a bad drawing. This point -1, 2 is probably going to be a little off that line. All right, looks like it's off the line. Now, let me show you where this whole determinant thing comes from. What they're saying about the determinant of some matrix being equal to 0. If I mess with this, 7/4 equals 2, and if I get everything to one side here, alright, and if I multiply by 4, that would be 7 equals 8. And if I multiply both sides by 4, so you can clearly see that this isn't working out. And then take everything to one side. Say I subtract 8. So that'd be -1, equals 0. Again, clearly not. Clearly not. But when I take everything to one side, what you're going to notice is that this thing here, this number on the side, this number on this side, will be either plus or minus the determinant of that matrix that was in question. All right. And let me show you. Okay. No, actually, no. Nope. Sorry. That's not the determinant. Look at me making statements that aren't true. So ignore what I just said, but still, we're seeing that through all these calculations here, these are not collinear. All right. Now, let's go through the procedure they gave us, and we'll also see, through this statement. And again, back to this statement here. We're looking for this determinant, right? The determinant of this matrix, where I put the points that were the 3 points in question down the first 2 columns, and then a column of 1s. And if that determinant is not 0, then they're not collinear. So based on what I just said, okay, based on all this work here, we're seeing that no, they're not collinear. Right. And if they're not collinear, I know where I went wrong with this statement. It's because I simplified the fraction. Take this here and do cross products, right? That'd be -16 equals, -14, which is clearly false. And then add 14, you get -2 equals 0. Yeah, it's before simplifying, right? So if I don't simplify, it's this number here. That'll be plus or minus the determinant. Right, before I simplify. That's better. Right? I'm telling you that's always going to happen, and I'll show you with another example after this. All right, but let's see. So I take the determinant of the matrix where I just put these points 1, 5, -3, -2, -1, 2, and then a column. I put the 3 point coordinates down the first column, and then I put a column of 1s. All right, and let's find this determinant. So again, you would copy the first 2 columns, do all those diagonals. I'm just going to come back with it when I'm done. All right, so I wrote the thing and all that and did this, and The determinant is -2, which remember I said it was going to be this thing, right? -2, when you get everything, if you do the slope equals slope thing and don't simplify, and you do the cross products, take everything to one side, that number on the one side that's not, is on one of those sides is going to be plus or minus the determinant of this matrix here, and we're seeing that it is indeed -2, which is not 0. All right, and since this determinant of this matrix where you put the 3 points down the 2 columns there, and then the column of 1s, since this determinant is not 0, the points are not collinear. They do not fall on the same line. All right, so again, my little hand drawing was a little off. Right? They're not collinear. I mean, I guess if I had graph paper, it would have been better. You could have easily seen that they were not collinear, but I did not have graph paper handy. I apologize. All right. All right, so let me do that again, all right, with the next set of points that they give us. All right, so again, they're asking, are these 3 points on the coordinate plane, are they on the same line? Are they collinear? Again, that'd be the same as asking this question. Is the slope of the line going through these 2 points, 4 minus 0 divided by -5 minus 3, is that equal to the slope of the line going through these 2 points? 0 minus 2 divided by 3 minus -1. And let's see, what do we have here? Again, I'm not going to simplify this time. 4 over -8. Is this equal to -2 divided by 4? Yeah, these are both -half. And if I do cross products here, we'll have 16 equals 16. Right? 4 times 4, -2 times -8. And then subtracting 16, we get 0 equals 0. Yes, these are collinear. And we're going to see that the determinant of that matrix will be 0. When I take I do the cross products of these slopes and take everything to one side, we're going to get either the plus or minus the determinant, but it's just 0 here, so there's no plus or minus 0. But let's double check. Right? Let's find the determinant of that matrix that they mention. So I'm finding the determinant of, I write the coordinates down the first 2 columns, -5, 4, 3, 0, -1, 2, and then a column of 1s. And I'll find this determinant. All right, so I'm just going to do this and come back when I'm done with it. Okay, so I did the thing, and some of those products were 0. I took all the diagonals going down to the right, added those up, and then subtracted all the products of the ones going down to the left, and I get 0. All right, the determinant of this matrix is 0, which we were hoping for, because we did say that the points were collinear. So these points do fall on the same line. The points that we are given are collinear. Wonderful. Okay. So again, just quick checks on that one. All right. Then we can also use, and again, you can do that. They have activity here where you're doing the same thing. Again, you can figure it out without the matrix, right? But you can still I would say try using the matrix to figure it out, because it'll just give you more practice in finding 3 by 3 determinants. All right, and then we can also use this determinant here to find the equation of a line. Now I know that you know how to find the equation of a line that passes through 2 points, or at least you better. I mean, you're in linear algebra now. You should have taken at least some sort of basic algebra class before, where you find the equation of a line going through 2 points. So the way we're doing it here, again, just to practice taking 3 by 3 determinants, is I set up that matrix again, where I have the 2 points that I know, right? The 2 points that I know, and then some third point that I don't know, right? X comma y, some variable point x comma y. And again, you got this column of 1s here, and I set it up so that the determinant of this matrix is 0. So I write this is an equation. The determinant of this matrix is 0, and that means that this unknown point is on the same line as these 2 points, right? They're collinear if the determinant of this matrix is 0. and then I solve for y, and then gives me the equation of the line. All right, so like I said, I know that you know how to find the equation of a line going through 2 points, or at least you should. So I'll start off, I'll just do one example here and call it a section. All right, so we're asked to find the equation of the line going through these 2 points, right? If you were drawing this, there's 5, 1 and 2, 6. All right, these 2 points here, and this line. Oh wow, that's terrible. All right. But this line, all right, we're trying to find the equation for that line. Now clearly it has a negative slope, and I know you can do this, right? The slope, remember this is the m was the slope. 6 minus 1 divided by 2 minus 5. This is negative 5/3. Right? The slope of this line is 5 divided by negative 3. And then just put that, you can put it in point slope form. Say I pick this point right here, do y minus 1 would be equal to negative 5/3 times the quantity x minus 5. And there you go. And then I can distribute this and put it in slope intercept form if I want, and then add the 1. So y equals negative 5/3 x, and then plus 25/3 plus another 3/3 would be plus 28/3. Here's an equation in slope intercept form for this line. All right. I know you know how to do this, right? This shouldn't be too difficult, but I still would like you to practice the way they've mentioned so that you get used to trying to find determinants of 3 by 3 matrices. So another way to do this, and I'll show you we get the same exact equation as I did here. I set the determinant of some matrix with these 2 points and some third point, some point called x comma y. All right, so this xy represents any point on this line, right? Like that, or that, or that, right? Any point on the line is represented by these variables. And then these other 2 points are on this line, 5, 1 and 2, 6. And then I got that third column of just ones. And in order for this point to be on the same line as these two, this determinant needs to be equal to 0. So I set this determinant here equal to 0. All right, and then I find this determinant. All right, and then we're gonna set it equal to 0. So I'll set this up. We got x, y, 1, 1, 1, 5, 1, 2, 6. All right, and then I do that thing right where I copy the first 2 columns. x5, 2, y1, 6. And again, we're going to set this equal to 0 at the end. Right? Now this here, I'm going to have x times 1 times 1 plus y times 1 times 2, so 2y, plus 1 times 5 times 6, right, 30, and then minus 5y minus 6x minus 2. And again, I want this to be equal to 0. And then I'm going to solve this for y. Alright, so look, I got negative 3y. Negative 3y. I've got negative 5x when I put the x's together. So I got those terms done, 30 and negative 2 make positive 28. And this is equal to 0. And then solving this for y, you'll see the exact same equation. Y here would be equal to, I'd add 5 divided by negative 3, that'd be negative 5/3 x. And then subtract 28 divided by negative 3, that'd be plus 28/3. There's an equation for that line, the line with those 2 points on it, 5, 1, and 2, 6, in slope-intercept form. And you see this is exactly the same thing I got using my old algebra skills. All right. So, same stuff. So I would still recommend, again, I know you know how to do it. I know you know how to find equations of lines going through 2 points on a plane. But try practicing this. Set this determinant here with an unknown point, x, y, and then the 2 points you're given and a column of ones. Set this determinant equal to 0 and solve for y, just to practice, finding the determinant of a 3 by 3 matrix. All right, and they got that example there. Another one. Now you here again, you have to, I'll leave this to you. If you were trying to do the same procedure to find the equation of the line that passes through these 2 points, which of these determinants would be set up, which of these matrices would you find the determinant of and set equal to 0, and then what would set that second part up, and then what would be the actual equation of the line going through these 2 points. And then you have a challenge activity where you're given 3 points, right, and asked to determine if the points are collinear. Let's see what the other levels look like. Yeah, this is the same thing. 3 points, are they collinear? And this one is find an equation to determine a line, the line going through these 2 points. So what would your matrix look like that you set the determinant equal to 0 for, right, with that x, y, and then the points, and then a column of ones. And then finally, what would be the equation in slope-intercept form here? All right, so I'm going to leave all that to you. And then you have your additional exercises, which some of these are part of assignment 6, some are not. I still would recommend that you do all of them because you can check your solutions, right? You can see the solutions here. Please work on the problem first. Try to figure it out first before you look at the solutions, because if you're just copying solutions, you're not going to learn anything, and it's going to make exam stuff tougher. All right. And yeah, so that's it for section 401, this introduction to 2x2 determinants, 3x3 determinants, and in the coming sections we'll see how to find determinants of larger matrices and just in general any square matrix. All right, so if you have any questions, let me know, of course. Hopefully this is a good guide for you, and thank you for watching.